Computer. Okay. Good morning. I hope you all had a great day so far. Let's start today's conversation. We are going to continue our discussion about transient stability analysis. In a previous session, we talked about the general concept of the transient stability analysis. We defined the meaning of the term transient stability analysis. We talked about the difference between transient stability and the dynamic response of a system, and moved on toward the mathematic equation, that differential equation that you could see on the screen as a classical equation, which we talked about that equation is developed based on the conventional rotary machine generators, and basically defines the dynamic response of our grid and each component in our grid. And we said if we have a multiple machines or multiple sources in our grid, the differential equation that we have would be expanded to a matrix form for each individual generator. We also mentioned that we don't consider loads in our transient analysis and the dynamic response because, as we defined, the time scale for transient event, or more specifically electromagnetic transient event and electromechanical transient event and steady state event, we saw that the time scale for transient event are much smaller, much thinner or shorter than the steady state time scale, which basically means that we are zooming in significantly in time, okay, to our dynamic. Therefore, we are able to assume that we have a constant load and we don't have any dynamic or variation in our load side. So that was why I said we are going to consider the generation part in transient analysis and consider the rest of the system as a passive kind of component or passive system. Now, if you don't have any question, I'm going to start talking about the effect of IBRs or inverter-based resources in the transient analysis that we talked about, the general form of transient analysis that we talked about. Any question, guys? No? Okay. So let's start. As you can see in the screen, we talked about the traditional swing equation. We developed that based on the synchronous machine or generally rotary machine. And we said with that swing equation, we could define the transient dynamic of our system. We had the equation of m second derivative of delta, and it should be equal to the mechanical power minus electrical power. Okay, that delta was the rotor angle. And we said when the mechanical power is greater than the electrical power, basically rotor speed is gonna speeds up. And you can see that when the Pm minus Pe is a positive number, meaning the second derivative is gonna be positive number because M is a positive also number, okay? So if the second derivative of a value of a parameter is positive, meaning that derivative that parameters basically accelerate. Because if you remember, let's consider the movement of any kind of like object. The first derivative of the space is velocity. The second derivative is acceleration. So we are talking about the change or movement in delta. So the second derivative is the acceleration. So if it's positive, that means the speed is going up, meaning the rotor speeds up. Okay. And if it's negative, which happens when mechanical power is less than electrical power, then we have a deceleration. Okay, so the speed is gonna go down. The rotor is slowed down. So this was our traditional, conventional kind of like swing equation that would define the dynamic of our system in transient time, in short time. Come on. Now, what would be what would happen to that system, to that transient analysis, when we introduce IBRs, the inverter-based resources, into our system? Let's uh, step back a little bit and talk about the actual like changes that the IBR would cause in our analysis from the IBR perspective. Okay, as we mentioned before, in synchronous generator or different uh, traditional, like generally the rotary machine resources, we have a physical rotating mass, which means we have a physical inertia. We have a natural inertia in our system. Okay. The transition challenge is the loss of from the IBR compared to the rotary machines, or the loss of this physical inertia. We define that inertia in previous week. We said that the inertia is basically the ability of the system to resist against change. Now, in transient stability, we are talking about the short time changes. Okay, very fast changes. So if we don't have inertia, that means our system is going to be under a significant challenge when it's going to deal with those fast transient, fast variation, fast changes. Okay. Now, inverter-based resources, more specifically grid following, also have to have a digitally handled control system and a PLL, a physical phase lock loop. Okay, so these two characteristics would, plus that lack of inertia, would create a different in the nature of those resources when you compare inverter-based resources and rotary machine resources. Now, how we could define our system, our new system, the inverter-based resources, okay, and represent it in a way with a parameter that we could use that traditional concept that we had for the swing equation, okay, and use that to analyze the inverter's behavior in our system. Now, to do that, we are going to define, as you remember, that swing equation was the dynamic of the delta, the rotor phase angle. Okay, now in IBRs, because the delta that we have in rotor, let me restate that in a better way so you could understand that delta that the rotor has in rotary machine, we said it depends on uh, mechanical power, the difference between mechanical power and electrical power. Okay, now let's put the equivalent to those parameters. We had delta, which we are going to see at last what's going to be the equivalent of that. So that equation was m d squared delta over dt squared equal to p mechanical minus pe. Okay, now in grid, in a IBR integrated grid, we don't have mechanical power and we don't have this inertia. Okay, and we don't define anything as electrical power, like specifically. Okay, but what we have in inverter-based resources, okay, we have our input power, which is the power of the inverters, okay, and we have the grid power, what the grid demands. Okay, now in the control system, when we talked about the grid following, we said in order to inverters to meet the demand of the grid, okay, we are changing the theta in our inverters. So we could say that the difference between these two theta, theta of grid and theta of inverter, okay, could represent the power variations, okay, or power transfer or power fluctuation between our source and our reference. So these two could be represented as equivalents of PM and PE. So if the thetas are representing these, we could basically use the theta of our inverters and the theta of the grid to represent what the concept that we had before in conventional swing equation as mechanical power and electrical power. Okay, now if this is representing, these two P's are representing these two values, okay, we can define the difference between these two theta as our delta, as this delta, and say, okay, the same swings or variation that the rotor angle had in rotary machine, okay, or in synchronous generator, okay, now we are gonna see if we have a variation in power, okay, in between the inverter's power and the grid power. If we have any variation between these two, okay, the result of that variation is change into the difference of those theta or the delta P that we define. Is that clear how we make the equivalent between the rotary machine parameters and inverters? Is that clear? Anyone in the Zoom link, do you have any problem with that or any question? So if not, okay. Now we defined a delta based on the theta of the inverters and the theta of the grid, okay, that represent that virtual rotor angle, okay? Now that we have an actual, like a virtual rotor angle, okay, we could use that swing equation, that second order differential equation, in order to calculate or like to analyze what's going to happen in our system when we had a fast transient. Now, when we talk about the grid following inverters, if you go through the uh, state equations and basically the system function for the control system and topology, okay, we can represent the dynamic of that virtual rotor angle. Again, please pay attention. This is a virtual rotor angle, delta P, okay, with another second order equation, which is the same, like the modified version of the previous one. As you can see in the screen, the equation, the swing equation, that describes the fast transient response of a grid following inverters, okay, in a transient state. It depends on the parameter that we say is t squared, the t, the psi, and the omega 0. What was those? What are those? T is basically the time constant of our PLL, shows how fast it would respond to any changes. Now, step back and think about the definition of the inertia. Okay, so if we have a very high time constant, meaning the PLL would respond very slowly to the variation. Okay, that means the overall system is more vulnerable, okay, to the changes. So if we have uh, uh, a shorter t, okay, meaning we have a lower inertia. And if we have a higher t, as you can see in your system, we have a higher inertia. So system is resisting against the change, and we have a higher time constant. It's not easily changed by any variation at the output. Is that clear? So let me explain it again. I wanted to make sure that everyone is clear on that. More resistance to the change. Is the definition of the inertia is the ability of the system to resist change. Okay, so now if we have a higher T, that means when any variation is injected into our system as an input, the system would react to that slower. That means the system is heavier, if you want to like consider that as a physical system. So we have a higher inertia. Now, the psi that you see in our system, in our equation, is the damping ratio of our PLL. You remember when we talked about the PID controller? The damping ratio was the ability of our PID controller to reduce the errors to get to the new steady state. So that also could represent the same damping factor. It's basically literally equal to the damping factor that we had in rotary machine. Omega 0 is the nominal frequency, okay? And the omega grid and omega PLL is, I think, is self-explanatory. The omega grid is the frequency of the grid, which, if you remember, when we talk about the power equations and power flow equations, we said, okay, the P and omega are related to each other. So it's basically represent the power of grid. And the omega of PLL is the frequency that the PLL defines for the inverters. Okay, so it's going to be basically representing the power injected or like consumed based on the omega of grid. Are we good so far? Any question? No? Okay. Now, what would be, as you see in the equation, most of the effect when we're talking about the transient analysis is from the parameters that relates to the PLL. Okay, but if you remember in grid following, we had PLL and we also had a PID controller that controlled the current. Okay, so I want to ask you if you have any suggestion that why the swing equation are dominated by the values related to the PLL, okay, rather than that current control or like a power control that we had in our grid following. Anyone has any guess for that?
Because it's setting nodes or controlling them.
Both of them are controlling. Okay, the PLL is controlling the frequency or synchronizing the inverters to the grid. That PID controller are meeting the load demand. Okay, and changes and addresses the change in the load. Okay, so now in transient analysis, we thought that the swing equation is dominated by PLL values rather than the PID controllers that answers to the demand of to the change in the demand. Now, why is that? Why that PID controller that addresses the change in the demand would not uh, uh, present itself or affect our swing equation when we talk about the transient analysis. Between my statement, I already gave you the answer. Okay, but anyone can point it out? No? What was our assumption regarding the loads when we talk about the transient analysis? We said our load is constant. We assume the load doesn't change. So if the load doesn't change, that PID controller basically doesn't work in the transient time scale. Okay, so that means that that PID controller would not affect, because the time scale of that PID controller is much larger than the transient time scale, so it would not affect. But PLL would, because it's dealing with the synchronization and the frequency variation. Okay, now let's talk about the discussion about, okay, now that we know that the PLL would have that effect, what would be the role of the PLL on having any instability? So how would it affect our transient analysis result? Okay, transient stability analysis result. Now, we already said that the PLL is also a sort of PID controller or like a PI control. This is kind of like a closed loop feedback loop that tries to synchronize the frequency, and if you have an error, it tries to eliminate that error. Okay, now what happened is that if we have a weak grid, okay, if we have a weak grid, the reference for that PID controller, okay, is not stable because the grid is not stable enough, is not strong enough to have a strong solid frequency. Okay, now in such a condition, any poor tuning of our PLL control system, meaning that we have a poor kind of like tuning for KP and KI in our PLL controller, okay, would result in an oscillation. What that means? That means that you have a chaotic behavior in a weak grid scenario in your reference. Okay, now if you have a not properly tuned PLL and you have the weak grid, the two combined with each other creates a nonlinear oscillation. So there is not going to be any damp in our system because the grid itself, the reference itself is varying, and we define our PI controller in order to like work in a stable scenarios to reduce the error. Now, not only it tries to reduce the error and it fails, but also the variation in reference would add up to that failure. So we are going to end up with an oscillation. And as you can see in the loss of synchronization, basically the voltage instead of being a stable, or at least being how to say, a linear kind of like function of that error, now it become a nonlinear, okay, more complicated function of that delta P or that error that we have in our frequencies. Now, there is one parameter that we define when we're talking about the PLL in grid following, and it's the maximum delta that we get. Okay, when we're talking about the weak grid, we said in the beginning of our discussion, if we have a weak grid and poor tuning, it could result in oscillation. Okay, so it's not guaranteed that any weak grid scenario is in a stable for gate following, okay, but it could get to that point. Now, there is a maximum delta, a maximum error, okay, that could happen, okay, and the system still be able to like reduce the error, handle the situation, and remain stable. Based on the parameter, we define that maximum angle as maximum allowable power angle. That basically is a threshold that PLL could keep the inverter synchronized to the system when we are dealing with a weak grid scenario. If we pass that delta, meaning the error is large enough or oscillating or uh, uh, behaving critically or chaotically, then the PLL would not be able to follow the errors and would not therefore would not be able to like synchronize to our system. Are we good so far? Okay. Any question? Now, in inverter-based resources, we could define a parameter as fast frequency response. Okay, that basically defines synthetic inertia, some sort of kind of like a concept like that, a synthetic or like a virtual inertia. Okay, that defines how good an inverter could tolerate the changes and not get unstable. Okay, that power for fast frequency response is defined based on the frequency loop gain, the nominal gain, and the frequency of the grid, which is the instantaneous frequency. Now, if several IBRs respond to a certain variation in frequency and their KF is too high, meaning they are responding harshly and not synchronized with each other. That would result in oscillation or a significant overshoot in the frequency, which basically means we are going toward the instability. So far we are talking about the effect that the inverter, or more specifically a grid following inverter, could have into our transient analysis. Okay, but how about the grid forming? Grid forming, we said it's work with the loop control generally. Okay, and as you can see, it doesn't have the PLL. So would it mean that we don't have any swing if we don't have a PLL? Because in grid following, uh, we said that other control system that controls the load is not basically affecting the transient equation. But now that we don't have a PLL, would it mean that we don't have a transient in our grid forming inverters? The answer is no. Why is that? Because the grid forming inverters is not designed specifically to answer the demand. It's designed to mandate the voltage level and the frequency level. Meaning all the transient, every part of the control system in grid following is actually now showing effect in the transient analysis. There is no demand control, basically, precisely in the grid forming. So the group control would affect directly into our transient equation and the swing equation. Now, similar to the grid following, for grid forming, we also define a virtual swing equation. But here, we define it differently. Back then, we knew that, okay, the swing equation is affected by PLL. So we were very kind of like, it was very easy to incorporate the PLL specification and define exactly what is the swing equation. Okay, in this scenario, we basically try. Okay, I want to like emphasize that we basically try to come up with an equivalent model based on the behavior of a rotary machine. Okay, and try to define an equivalent model for the grid forming inverter to analyze their transient response. Now, the logic behind that is that the grid forming, similar to the rotary machine, they are their main control kind of like configuration is to keep the voltage and frequency stable. And they both would mandate the same parameters. Okay, now based on that logic, we could provide the equivalent, the same, similar to the swing equation for the rotary machine, for the grid forming inverters. We call it a virtual swing equation, and it's exactly similar to the swing equation of the virtual machine. Now, here, the M, we call it MV, is not an actual physical inertia. We call it virtual inertia. Same as D, the damping factor here is also virtual, okay, because we don't have damping factor. We just say, okay, because grid forming works like synchronous machine or like a rotary machine, we could say, okay, the grid forming behavior could be represented with an equivalent damping factor. Okay, part of it. The theta is what we discussed before, the internal voltage phase angle, okay, which defines the difference between the grid and inverter phase angle. P star is P reference, or what we call it before, mechanical power. It's going to be constant. And the P is the P out, the one that oscillates. If you remember, PE was oscillating as a sine kind of like function, and PM was a constant function. Then we talked about the general swing equation. Now, how we could find those MV and DV and all those things. Okay, go ahead.
Where, um, where does the internal oscillation come from? Where does it happen in inverter?
For the inverters, doesn't matter is it the inverters or any kind of system. Okay, you have a system that have a feedback loop response to uh, fluctuation.
Right, but I'm
Okay,
just wondering
sure.
where that is.
Uh,
Like, is it just like reflection at various points in the grid that come back and create the oscillation? Like, where is that?
it's the oscillation is how in the response of the controller toward any injected input fluctuation that it reads from the grid. So we have like a short circuit in the grid, okay, or any kind of like fault in a grid. So what inverter sees at its terminal is a fluctuation in voltage and frequency when there is a fault in a grid. Okay, the control system is designed to automatically follows those fluctuations. So it has a reference. It doesn't understand that there is a fault. It says what it sees is that okay, my voltage and frequency is changing, so I have to
So this is the
adopt.
control.
Yeah, yeah. So that define the response of the control system in inverter would create that transient swing equation. Now, back to the equation that we had mv d squared, the second derivative of the theta dv, first derivative of the theta, and then rp. Now let's define what are those md and p's. Now, mv, which we said is inertia of our system, okay, is basically could be calculated based on the variation in power, the delta P, okay? So you have a droop control. You have a reference power, you have a measured power. The variation of that measured power is delta P, creates delta P, and the denominator for calculating the MV, okay, is the margin or how fast you allow the frequency to change. Does that make sense? So you have a droop control. It sees variation at the input, but it doesn't mean that it answers instantly. We said, okay, we have a definition, we have a tuning to do in our control system. So the control system has a speed to respond to any variation. What was that speed? When we had a delta P, it would try to like adjust the frequency. So there is a certain speed in adjusting to the new frequency. That d omega over dt is that the speed of the controller in order to respond to the changes and adjust to the new frequency. Okay, now look at it from the inertial perspective. You have an input, you have a fluctuation, okay, and you have a speed to answer to that fluctuation and try to relate that with the definition of the inertia. The inertia was the resistance of the system to any changes, the ability of the resisting against changes. If you think about that, you could understand why we could define mv as equal to the delta p or the speed of our frequency change. Okay, now uh, how we could define our damping factor. The damping factor is directly relates to our control system, to how our PI droop control system works. Okay, so in the droop control system, we define Kp as the parameter, as the droop gains, and it basically defines the damp in the error that we have. It easily could be seen in our equation. So we have our measured value, we have our reference, okay? We have the delta P, the variation, and this is minus Kp. So if the Kp is high, that means it fastly reduce the variation of the P in this equation. So this variation would be eliminated fastly. If it's slow, if it's low, it would take more time. So we could have, you could address these changes, these variations. Okay, so we could define the dV or damping factor in our previous uh, equation, okay, based on 1 over Kp. So now in this equation, we have both dV and mv. Now, in some uh, uh, textbook, they use psi and h in the swing equation, okay, instead of mv and dv. Here, I represented the how you could calculate the psi and h based on the mv and dv, okay, and this k is basically the uh, system characteristics. As you can see, is the voltages time divided by reactance, okay, when the delta is 0. So it's going to be the differential, the speed, the rate of change between P and delta. How power, active power is related to the change in a phase angle. Any question regarding that? And okay, this S base is the nominal power of our system. Okay, so nominal apparent power, which is S, not P or Q, is S. Go ahead.
So I know you have virtual damping, but the filters that we put in the system, obviously I'm thinking what I model in MATLAB. Are we getting damping from those, or is there,
Two different things.
okay,
This damping factor defines the fast transient of your phase angle. You create a fluctuation in your system. That fluctuation would create a very fast change in your frequency or your phase angle. This damping factor is the ability of your control system to address that fluctuation. What filter does is the ability to eliminate the high frequency variations.
so we don't count, we don't consider that.
No, filter, and as you can recall from our previous segment, we said one of the differences that it makes the transient between transient and steady state because of the time scale is that the transient normally happen in a millisecond or microsecond. So we don't have any frequency in transient state. Okay, so basically the concept of the filter doesn't mean anything in transient state because we don't have any frequency. Filters are response to the frequencies, to different frequencies. So if it's low pass, it would let the low frequency pass and high frequency get damped or eliminated. If we don't have any frequency, basically we don't have a meaning for a filter.
I just figured even if that small time scale, still high frequency coming through, and that would be the only thing that would get there. It would be the slow.
You call it high frequency, that's not very precise. I know it's sometimes I see that. Yeah, I see that also. I see that the same kind of like terminology used for very fast fluctuation or very fast disturbance as a high frequency disturbance. That's not a good terminology to use. High frequency needs repetition. Frequency needs the definition of the frequency is how many times we would see a repetition of our system within 1 second, right? So when we have one fault, that fault is not happening over and over again. So there is no frequency. It's one instant, very short time disturbance. So there is no high frequency. The reason that they use high frequency is because of the time scale. Okay, so if, for example, you have a very sharp, let's say, very sharp, this is our frequency or voltage, and we have a very sharp kind of like disturbance. Okay, this is a function. This is a function of time. Okay, using Fourier series, you can represent this as the summation of some kind of like a n cosine of n omega t plus some theta plus b n sine of some omega n omega t plus theta, right? So if you have such a sharp kind of like, yeah, and you have a very sharp disturbance, okay, what would happen in frequency in this Fourier series of this time function is that the most of the values that you see in an and bn are related to the very high frequencies. This is kind of like the mistake that they make when they define a transient disturbance as a high frequency effect. Because in Fourier series of those disturbance, you would see more higher frequency than lower frequency. But remember, Fourier series is just a mathematical equivalent, it is not something real.
But
Is
it's
that
modeling.
it's modeling was, yeah, exactly. You see, you have two apple. When you want to like mathematically model it, you use the number two. Number two is not apple, but it represents the two apple. You know what I'm saying? It's the same thing. You have a Fourier series. You define an actual thing. This is what happened in reality. But in Fourier series, you would see some sinusoidal. This is not what's happening. You represent it with a multiple sinusoidal because for us it's easier to deal with sine rather than this arbitrary function.
I'm just thinking the reason why is because I thought basically what that was saying is that that means at that time, we have a very large frequency disturbance where it's like, instead of it being like this, we have
Two,
a
two different things. Okay, two different things. You are talking about the high frequency or frequency disturbance. Yeah. Let's this the kind of like divide these two concepts. Okay, distinguish them. One concept is high frequency, meaning all the variations that happens with a very high hertz or frequency within 1 second. So it happens like, for example, 1,000 times or million times in 1 second. This is high frequency. Frequency disturbance is that you have a frequency, so it's 60 hertz. Now, for any reason, your system malfunctioning or there is a disturbance happening to your system, that this 60 hertz suddenly become 40 and come back to the 60. So frequency disturbance, high frequency, two different kind of like concepts. Okay, so distinguish these two. What we're talking in the swing equation, okay, when we say disturbance in frequency or disturbance in voltage, is the fast change in one frequency that we have. Okay?
Not.
Yeah. Any other question for guys in the Zoom also? No? Okay, so by these equations, you basically can calculate MV and dV, and you have a virtual swing equation that represent the transient behavior of grid forming based on the logic that we said. Okay, now I put an what was the name of this sign? What is the name of this sign? Exclamation or
Yes.
yeah? Okay, I forget my pronunciation. So I put this sign here for a reason. It's just only one. Okay, here. And it's because I gave you a reading assignment. I urge you to like go through that paper again, that duality between GFM and GFL. Okay. What we discuss here is a standard understanding of engineering that we could represent grid forming transient behavior with that virtual swing equation. Okay. But in reality is much more complicated than that. One of the byproduct of that paper is to deny such an assumption. So in all the analysis that you see, the models in MATLAB, all the analysis that you see in the papers, the general standard papers, they're using this virtual swing equation to analyze the behavior, the transient behavior, or like a dynamic response of a grid forming inverters. Okay, but it's not accurate. The paper discussed that, and it's very too much to kind of like get into the detail of that. But I just wanted to like you have the idea that you can use that and you will use that, but it's not the right answer. And if you read that paper, you could find out why. Okay, I also put an example of like how that works. This is kind of like the repetitive kind of like situation. So basically, to summarize, we said that, okay, we have the general swing equation, okay, and now that we have inverters integrated into our system, we need to modify, like what we did in Powerful, we need to modify that general swing equation so we would be able to use that analysis for our grid integrated inverters. Now, we said because of the very basic difference between the grid following and grid forming, we can deal with those two similarly. Grid following, the sensitive transient part are basically the PLL. So what would be dominating the transient response or the dynamic response in the grid following is going to be the PLL factors, PLL configuration, the PLL parameters. Okay, and we saw how it would develop the swing equation for grid following. But in grid forming, we don't have PLL. Instead, because grid forming is designed to respond or mandate the voltage and frequency, basically the whole group control system are going to be involved in the dynamic response. So any disturbance would directly go to the main control system, to the group control system. And we saw how we could use the virtual swing equation in order to define the transient analysis or the transient response of a grid forming inverter. Any question? Oh, sorry. Yeah. That's one. Yeah, sorry. Yeah. Any question? No? Okay, if there is no question, that's it for today. Thank you very much and have a great rest of the day.